Howdy folks, I'm Ferris Equus, and welcome to part 2 of West Coast Rail Nerd Reacts, a series where I go through and comment on Hyce and kAN's Railroads Online content. As you'll remember last episode, I made the deeply flawed decision of deciding to do math without much preparation, and what that turned into was a weeks-long journey into the I want to say fascinating, the fascinating mathematics behind journal bearings, both plane and roller bearings, as used on railroad cars. And to this video isn't going to be in the same style as the previous one is, where I was in my own little corner of the screen and then I was reacting to the video that was in front of me. This video is a lot more tailored to go through bearings, railroad bearings, and how they work, and the differences between the two. And not to give too much away at the very beginning, but the results are going to surprise you, because they certainly surprised me. But before we get that far, let's go ahead and have a little review of what bearings are. In this episode that I was reviewing, so we tried running A Train with No Locomotive by Hyce. They actually do go through a brief description of the different types of bearings that are used on train cars, specifically plane journal bearings and roller journal bearings. And the difference between them, well, here, let's take a look. I actually shot some footage at one of the railroad groups that I volunteer with. They have operating rolling stock, and they just so happen to have equipment that I could film. So let's take a quick look. So let's take a look at a plane bearing. So this is the journal box. It holds the axle and the brass and everything else. The wedge. And this is the journal lid, this thing up here. And you can see that this is the axle. This is the thing that actually rotates around and around. It rides on this brass, and it's stuck in there with this thing called the wedge. And that is the oil that gets dragged around the axle and creates a protective film that the axle rides on the brass. And of course, your number one job is to try and make sure that there's enough oil in here that it actually gets put onto the axle. And one of the other things that I forgot to mention in this short little video clip is this thing down here is actually the pad. We use journal pads on this railroad operation, and it makes it very easy to keep these things lubricated. Your alternative is to just stuff a whole bunch of like cotton mop material in there. But the problem is if you don't pack it correctly, it tends to get wrapped around the axle and creates all sorts of havoc because it's not actually putting oil onto the axle, which is problematic. If you don't have oil, you got a hot box, and hot boxes ruin trains. So don't do that, especially on these old ones. Then close it, you just clunk, and it's done. So let's. So moving on, this is a passenger car, about 1950s vintage. And this one is slightly different. And this, by contrast, is a Timken taper bearing pack. These come in big long sleeves, and this is the cap of it. And you can see that there's no oil, there's no nothing. And instead of having a box that all the oil sits in, it's just the bearing. I'll show you some pictures and some video of what these look like without the cap on, because obviously you can't see anything. And with these guys, and that will come up in just a second, by the way. Right after I finish going through these videos, I'll actually cut to some CAD models that'll show us much better detail of what's happening inside this bearing pack, because as you can see, there's not much to see on the outside of it. All you have to do is there's a oil port here, a grease port, And every few thousand miles, you repack the sucker with more grease, and then you send it on its way. So unlike the plain bearings that we saw just recently, all you have to do is fill these with grease, and you run. A lot different. And this.
And then I have one more video.
And here we are with a freight car. And you can see that those taper bearings look a little bit different than it did on the last video where I was taking a video of a passenger car. This one doesn't have anything supporting it at the bottom down here. And it makes it very easy because all you have to do is lift up this truck frame and the wheels come out. And it makes it very easy where all you have to do is pull out the wheel set and drop a new one in, and it makes maintenance very, very, very easy. And you can see that they've even eliminated the grease port. And all you do is you run directly on the bearing surface here, which is insane. Don't need to do any of that maintenance stuff. Just take out the whole wheels and put some new wheels underneath it.
So that was a quick look at what bearings look like on the railroad nowadays. And to break it down a little bit, to give you some context, plain journal bearings were in use since the very beginning of railroad operations. It doesn't get much simpler than here's an axle that rotates the wheels, and we're just going to put something on top of it that's going to bear the weight. So the technology changes a bit. They get into different types of bearing materials. They get into different types of oil that they put in there. But by the end of, until about the 1940s, 1950s, they don't really invest too much. Most train companies don't invest too much into trying to get taper roller bearings onto freight car equipment. And it's not until the late 1950s and to the modern days that you get tapered roller bearings on everything. In fact, it's currently an interchange rule that you have to have roller bearings on your equipment if you want to interchange it between railroad companies. And there are a lot of complicated reasons for that. But just to note that it is the standard now. Taper bearings are what you'll find on almost all railroad equipment. And per that last video, it actually comes in one solid assembly now where the wheels are connected to the axle and then the bearings are pressed onto the ends of the axles. Actually, I can show you just about now. And to do this, I'm actually going to hand it over to my future self. Hello, future self. Who's going to show you some CAT models of plain journal bearings in probably the smallest railroad equipment that you're going to find on standard gauge, and roller bearings that I've modeled. So take it away, future self.
Hey folks, Future Ferris here, and here I am, an inventor professional, my CAD program of choice, and I have in front of you the tender axle assembly off of the Jupiter replica. This is based off of an 1860s pattern of journal axle. And then I also have a 1970s to modern era journal axle assembly off of a modern freight car. Specifically, the prototype for this one is a 1957 80-ton flat car. And this is the tender assembly off of the Jupiter and 119 fame. And as I guess the first thing that you can see between the two of them is that the 80-ton assembly has a much heavier axle. I mean, it's nearly 3 times as thick in some places. And the standard axle of the 1860s is much thinner. There are other changes, and I'll show you in just a sec, but just to point out that there's a huge difference between the weight carrying capacity of an 80-ton axle and that of a tender axle for basically an 1860s locomotive. So to get started, here is the axle assembly off of the Jupiter. And as you can see, this is the journal box. This is what actually holds all of the assembly inside of it. It's
if you remember back to the video that I just showed, this is what actually holds the axle and the brass and the wedge. And if we tilt down inside, there's not actually any oil there, but this is where the oil would be. And to give you a better view at what would be inside of what this looks like, and the reason I brought you into CAD, is that I can actually take a section view of what's in this model and show you what's inside. So if we look at the axle and the assembly that's there, you can see the journal box. The oil is contained down here in this bottom section. Here's the axle. This is the part that actually moves. This is the brass, which is what the axle sits on in the journal box. And this is the wedge that keeps this brass in place and holds the journal box assembly together. Because once you put weight on it from the top, all this sandwich gets squished together. One interesting thing to note is that there's actually a locating feature on this axle, which is this front lip. This actually gets eliminated when we go to the larger axle, and it means that this brass actually can move back and forth very slightly. I don't have it modeled that way just to try and keep things simplified in my model, but theoretically you could move this back and forth. And one of the things to notice is that there's actually a lot of places for this oil to go. So if we fill this portion up with oil, you'll notice that there is actually a gap here at the back of this journal. And you can put a wiper here or some sort of axle locating assembly. And it's meant to try and prevent oil from just like falling out the side and onto the wheel. But what you'll find with heritage railroad equipment, and with railroad equipment in general, is that the seals that are on the axle don't work all that well. They wear out over a certain amount of time. And so it just sort of, the oil just sort of leaks all over the place. And it's not exactly a great experience. You have to clean it off eventually. And it makes your rail dirty, and it makes it slippery because it's oil. So there are any number of reasons why, this isn't as leak tight as you would think it is. In contrast, let's go over to this 80-ton modern assembly, and let's take that same section view, and let's see what we can see about the axle. So the axle actually now has bolt holes in the end of it, and these bolt holes make it so that you can screw this bearing assembly onto the axle. Instead of having a locating feature at the edge of the axle that prevents the bearing from sliding off and that prevents the journal from falling off, that's actually no longer needed, because this bearing assembly is pressed on to the axle itself. And it's important to see here that I've actually modeled this entire bearing assembly is actually one piece. And if you talk to SKF or Timken, the manufacturers of these bearings, they actually sell you a complete bearing pack. And it includes all this stuff inside of it. In fact, let's open this up and see what is inside of it. So here's what's inside of a modern Timken bearing assembly. If you remember the video that I just showed not too long ago, this is the cap. This is the cover of the bearing. And it makes it very hard to see inside of the bearing when you look at the front of it. But if we go back to this section view, I can show you what's inside the bearing itself. And what you'll find is that you have 2 rows of taper bearings. So they're not quite cylindrical, but they're slightly tapered to the inside. And that means that you have much more control over whether it moves side to side. from this view. And so here are the actual tapered elements. Let me grab that one as well. And as I rotate in 3D, you can see that that's actually what's carrying the weight of the car. And what that means is that the contact area, let's go back to our journal assembly. The contact area for this journal is this entire surface, this entire surface area. Let's open up this bearing, and I'll show you directly. This is the surface that the axle rides on, and there is a lot of surface area there. And so you can imagine that if there's no lubrication, that you're directly riding steel on brass, and that creates a lot of heat. That's actually why you get hot boxes, is because you run out of oil, or you've not lubricated it properly, or there's something else wrong with the bearing, and you just create a lot of friction because you have a lot of friction area. And the reason that mechanical engineers like roller bearings is because you've replaced that entire surface area with this little tiny contact area right here that's at the top of this roller bearing. And it's the interface between this roller bearing surface and this part, which is the cone. And you greatly reduce the amount of surface area that is in contact with one another, and that also reduces your friction. So I hope that this has been informative. Here are the different pieces. There are other things in here like wipers and seals and things that try to keep the lubricating grease and oil inside of this assembly. And if we look at this axle assembly, you can actually see sort of the path that it takes. In that second video that I showed, there was a grease port right here at the end. And if you follow the path as it goes through, you can see that it starts here, it goes through this space into the actual bearing assembly, and then it comes out the back. And on your plain journal bearing, the oil comes in here. It gets dragged by this axle because the oil does naturally adhere to it, and it gets dragged onto the brass, and it creates that thin film that the car actually rides on. Thank you, future me, for going through and creating those CAD models, along with the cross sections to show you guys what are inside of bearings. Let's move on to everybody's favorite part, math. Okay, don't worry. I heard some of you trying to click away and desperately running the other direction. I'm not going to make us do a lot of math. I'm just going to show you a little bit of what's necessary to understand the difference between plain bearings and roller bearings. And to do that, I'm going to take you to probably one of the best technical resources you can go to for bearing technical data, and that's the manufacturers themselves. Both SKF and Timken are companies that manufacture roller bearings, and if you go to their websites, you can actually find full technical manuals that you can look up that'll tell you how to calculate these values. So this is SKF's website, and they have a free technical journal that will tell you everything you need to know. But the major takeaway that we need to understand about bearings is that it doesn't all happen all at once. There are actually different places in when you start running bearings. As you go from 0 miles an hour to 100 miles an hour, let's just take that, you actually go through different transition points along the way. So you can imagine that if you're at rest, you actually have basically static contact between your bearing surface and your journal surface. So the axle down here and the bearing on top of it is you actually have this very strong contact between them. The next layer is sort of a mixed combination of the two. It's sort of a semi-state. And it's when you have just enough oil between the two layers that they begin to slide across one another, but you still get this sort of face-to-face contact between the axle and the bearing face. And then finally, we get into what everybody is trying to get to, which is full film lubrication. And this is the point at which there's an entire layer of oil that's in between the axle surface and the bearing surface. And this allows, basically, this is the lowest amount of friction that you're going to get out of an assembly. And you can see that this graph is in friction moment on the y-axis and speed on the x-axis. And there's something similar for plane journals as well. This is for roller bearings, but there's something very similar for plane journal bearings, but the math is actually quite different. So now that we have that out of the way, let's take a look at the actual calculations. Here is the spreadsheet that I created because I didn't want to do all the math myself, so I forced the computer to do it for me. You can see that this is built specifically for the cordwood car in Railroads Online. I have the wheel diameter, which I estimated to be about 26 inches. That was somewhat standard on narrow gauge equipment. The full weight I have assumed to be about 30,184 pounds, which was taken from a spreadsheet that was released a few months ago by Railroads Online community members. Thank you very much for publishing that data. And then the bearing size that I've chosen for this journal is 4 1/4 by 8 inches. And you may be wondering to yourself how I happened upon that value. If you look at Railroads Online, it's much more likely that we didn't have a journal bearing this size. The cordwood card itself is based off of a different prototype that has probably 4-inch by 7-inch bearings. But unfortunately, the only apples to apples data I could get, that is to say that I have the same size journal bearing on the plane bearing side and the same size journal bearing on the roller bearing side, was to choose the smallest available commercial size that Timken and SKF make right now. And that data comes from the smallest journal, which is 4 1/4 by 8. So I chose that one. And it doesn't actually affect the calculations all that much. You do see slightly smaller friction values if you go to a smaller bearing size, just because there isn't as much contact between the two surfaces. To try and keep things fair, I've chosen the 4 1/4 by 8 inches. And the thing that I've left out of this entire video, and actually makes probably the biggest difference between the two, is that plain journal bearings use oil as lubrication, and roller journal bearings use grease. And this was done as a cost savings measure for the railroads, because when you have oil, it's very slick, it's very slippery. It's akin to cooking oil in its viscosity, so it's very light. And the problem with it is that it tends to get everywhere. If you saw in the cross-section that I posted earlier, you can see that the journal box itself just holds oil at the bottom of it. And you have to constantly add more oil as time goes on. Typically, you would have a brakeman run out with everybody's favorite slurry. In the railroad industry, we typically call it PB&J, because it reminds us a lot of, sort of jelly. But it's not as viscous as that is. In contrast, modern roller bearings use grease, a high load, heavy grease, which is more akin to toothpaste. If you've ever dealt with the stuff, it's very thick, it's very viscous, and it doesn't have the same properties that oil does. And seeing as those are both very important properties for my calculations, I had to go out and find some. So the lubricating oil that I've chosen for our journals is Chevron Journal Tech's HD57, which is a commercially available, many heritage railroads use this journal oil. And this journal oil is, again, very light, very, very non-viscous. As contrast, you can look up the modern AAR equivalent for grease, and that is this Shell Gaddisguard S3 AAR AP 1.5, which is, I have to admit, a lot less catchy than the Journal Tech's HD57. And so I've chosen this to be representative of journal greases, and I have chosen this Chevron Journal Text to be representative of plain journal oil. So those are the two major differences, and as you'll see, they actually have quite the impact on what goes on in our calculations. So now that I've gone through the assumptions that I've made going into creating these calculations, and the differences between plain journal bearings and roller bearings, let's take a quick look at the actual episode that inspired this entire foray into mathematics and see what Hyce and kAN have to say about plain journal bearings, because that's what really spurred on this entire endeavor. So I'm going to show you a quick montage and then we'll come right back.
Dude, if we are slowing down like this, it's crazy to me because this is literally rolling friction slowing us down.
Yeah, well, I mean, plain bearings, they have a fair amount of friction to them, so. And
Like,
it is cold out. It's cold and snowing right now, which does affect the efficiency of a plain bearing. So you would notice that they would roll a lot easier in the summer than the winter. So
It really feels like we have brakes tied. This is unbelievable, the rolling friction on this.
yeah. So what the point I was getting to earlier was, 2 people can push one of the 40,000-pound coaches with roller bearings. You could just push
2
it.
people.
2 people, that's it. And you would be hard-pressed to have an army of people get a plain bearing car moving. Like, they are very, very, very resistive to start moving. Once they get moving, you get kinetic friction between the journal and then the brass itself. So then it's easier to keep it moving, but getting it started...
Yeah, static friction is a pain in the butt.
friction, yeah.
Yeah, effort to make a really long, narrow gauge train just because the amount of rolling friction and interactions between the cars. Like, that would have been...
Yeah, you're
like,
starting to add a lot more wheel sets and a lot more bearings.
Right,
with the
and
smaller
the bearings
cars versus
sucked,
longer cars.
basically,
Yeah.
to put it. Like, if you look at, like, modern trains, you can run, 2, 3, 400 car trains because everything is so smooth that it doesn't take nearly the effort to pull it you would think it would.
No.
And welcome back. As you just heard, Hyce and kAN have quite a number of things to say about plain journal bearings, and how they believe it's the cause of their train slowing down as it goes down the mountain. So to try and test that, I created this spreadsheet using the formulas that I mentioned earlier in the video, and let's go through and prod at a few of the things that Hyce and kAN said. So the first graph that I have here is rolling friction force versus speed for plain bearings, and I have it at 2 different temperatures. I have one at a cold temperature. For the purposes of this graph, it's about 40 degrees centigrade, and I have a hot temperature, which in this case is 100 degrees centigrade. And there are more values that could be made, especially with Hyce mentioning that in very cold weather, the oil basically turns into grease. It becomes much thicker. And if you're using older types of bearing oil, you actually have the possibility of it freezing overnight, which doesn't make it any easier to start your trains if they're not rolling already. But the math definitely supports Hyce's comment, where you can see that with warm journal bearings, plain journal bearings, the friction is 50 times less, 100 times less than the values that are being given for cold journals. So when the bearings are hotter and the oil is hotter and it flows more easily, you definitely get less friction force over time at various given speeds. So that's good. That actually, reinforces the understanding that many of us have, which is when things are hotter in an engine or in your journal bearings, that it's probably going to run better with less friction. The next graph I'd like to show you is friction force plotted for all bearing types. So remember earlier when I said that there are different transition states for roller bearings? One of the problems that I had is that modern roller bearing calculations, as done by SKF and Timken, have all of these transition states built into the formula. But when you look at the old formulas that are used by Machinery's Handbook and Mark's Mechanical's Guide, which were the formulas that I had to use in order to get these calculations done, I actually had to split it up into different sections. So when I had to calculate static friction, I had to go find the formula for static friction. When I had to formulate, a mixed, there actually isn't a formula for mixed contact. So when the SKF bearing guide said, hey, you're going to have this sort of mixed case scenario where you have both, static friction and a little bit of oil in there, they don't actually have a formula for that in Machinery's Handbook. They sort of assume that you always have full film lubrication going on. And so that sort of mixed case is left out. But as you'll see, that doesn't actually affect the results all too much. But what the Machinery's Handbook does have is constant rolling friction for plain bearings with full film lubrication. And that's sort of the assumption that was given to most things. And what we can see is that here is the friction given for these different loading cases. So as with the last graph, I have both warm journals and cold journals modeled. This red line is the warm journals, and as you can see, it starts with very high friction when you're starting off because you have static friction instead of kinetic friction. And then it quickly drops down as speed increases because you no longer have, all that friction force and the bearings are warm. The blue line follows closely behind it. It has a little bit more friction as time goes on because it's not quite warm yet. But you can see that it's still not all that bad. The real interesting thing is when we look at the yellow line. The yellow line is based off of all those formulas that I showed you earlier. And because I've had to break it up into individual little segments, this is much more of an approximation than it is, hard science. This is exactly the value sort of thing. But remember, this is about giving context, and I'm not trying to answer questions, very, very specifically. I'm trying to give a little bit more generalized idea. And the interesting thing here, actually, let me show you. The interesting thing here is that I drew a graph. The graph is not actually the interesting thing. The interesting thing is what the graph has to say. So here's that formula or that graph that was just shown, but in a slightly different format. What you can see is that there's this blue line is the plain bearings, and this orange line, as in the other graph, is roller bearings. And what you can see is that there are two different cases. One is for starting friction, when you have static friction and you don't have all this, all these different, loading cases. And then we have rolling friction, which is after you've actually gotten the car rolling, how much friction do you have? And the most interesting thing about this graph is that actually there's a transition point right here that all of a sudden the plain bearings have less friction than the roller bearings do. And, for traditional bearing design, that doesn't make a lot of sense. And I'm flabbergasted. That's It's not exactly the result that I was expecting, and I don't think it's the result that most of us were expecting. But talking to a few of my friends, a few of my mechanical engineering friends at the railroad operations that I work with, actually our chief mechanical engineer looked at me and said, "Oh, no, that makes sense. You would expect." He actually expected that roller bearings would have more friction than plain bearings do. And the short answer is plain bearings use oil as lubrication, and roller bearings use grease as lubrication. It's more akin to, what would you rather be in the swimming pool with? Would you rather swim through water, or would you like to swim through Jello? Which, I hope that none of you have personally done that, because having a swimming pool full of Jello is probably quite expensive. But you can imagine what that would be like, is instead of, swimming along somewhat leisurely because you move quite well through water, is you would have to struggle a lot to try and move through Jello. And let's look at that graph one more time, the one in my spreadsheet. Because there's actually this is, again, generalized value, but it's about 10 miles an hour on this graph. At about 10 miles an hour, this red plain journal line dips below the yellow line that the roller bearing friction is. And I think that's pretty neat. So for all of you wondering, what the great reveal is, it's this. That at higher speeds, it's actually more efficient to use a plain journal using oil than it is to have a roller bearing using grease. This is, of course, a generalization to the extreme, because it only really works in this use case, where you have a plain journal bearing using oil and a roller bearing using grease. If you switch the roller bearing out to use oil in the same way that the plain journals did, you'd actually see a much better efficiency out of it. And that's noted. And it's important to remember that the reason that they got rid of oil was because it cost a lot to maintain it. So they went to grease because you can stuff it in there once, and then you don't have to remember to do it for another 50,000 miles or 100,000 miles. I don't know what those numbers are exactly. If you do, let me know. But, it's a lot longer, instead of, every time you run the car, you need to go put more journal oil in it, which, the maintenance cost of having a brakeman go and do that is immense. And you would need to change out, the shoes and the wedges. And with roller bearings, you just plonk it on and go. So the last thing that Hyce and kAN sort of touched upon was that the reason that they were slowing down had to be because of journal bearings, specifically the plain journal bearings that they had. To try and figure this part of, their conjecture out, I created another graph. This one is kinetic energy versus speed. And kinetic energy is basically, you have a car moving in a certain direction. It has a lot of momentum behind it because it weighs so much and it's moving, pretty quickly. And the way that you measure this is in energy, in this case, joules. And I've also plotted the friction energy. So you have the train car trying to move in one direction, and then you have the friction that's trying to slow it down in the other direction. So you have these two opposing forces. And to try and put what Hyce and kAN said into context, I plotted it out for a single cordwood car. And what you can see is that kinetic energy is just massive. I mean, like, humongous compared to the friction energy. I actually created a column in my spreadsheet to calculate this. I've called it the percentage kinetic ratio. And at 10 miles an hour, let's see, which one is that? It's this one. You can see that the percentage of, the rolling down the hill at 10 miles an hour, is that the amount of friction that you have is 0.002% of total kinetic energy. So you're not actually losing all that much energy, because you're going, basically the car has so much mass behind it, and so you're not losing all that much to friction. So that sort of begs the question: what is causing all of that friction loss? If it's not the plain journals, what else is there? And the general answer is, well, actually, I don't want to say the general answer, because that's the problem. Is it's probably a lot of other factors that are causing Hyce and kAN to slow down as they go running down the railroad. Going around curves causes a lot of energy loss because you're changing direction. And when you change direction, the car is trying to move one direction, but it continues to want to go forward. And so it's imparting the weight of the car that is changing direction, travels through the wheels onto the rail, and the rail pushes it into the ground. And basically you're trying to move the track, but because the track is anchored, the car is forced to go around the curve. And you actually lose a surprising amount of energy that way. I didn't do those calculations because that is a lot of math. And if you thought the amount of math that I did just to come to this conclusion was a lot, it's a lot more work to start plotting things in 3 dimensions. And of course, considering that they're not point masses and all those other things that I sort of had to assume for this calculation. Hey audience, if I've cut to this section of film, it's because I probably went on a very long-winded tangent that doesn't actually explain very much. So let me cut to the chase and briefly recap everything that we've done in this episode to try and show the difference between plain journal bearings and roller journal bearings, and to critique the assumptions that Hyce and kAN had when they created that episode of Railroads Online. So if we go to the spreadsheet that I created, we have this graph that shows kinetic energy versus speed. This graph shows that the kinetic energy of a single cordwood car rolling down the tracks at a given speed is enormous. It's many hundreds of times larger, thousands, in some cases millions of times larger than the friction that's acting on that same car at the same time. So it's probably not correct that Hyce and kAN assumed that the reason their train was slowing down was due to journal friction alone. It's probably due to different circumstances that they are losing speed as they go down the track. The next graph that I have, which is friction force versus speed, is the graph that shows that, very much to my surprise, and I think to the surprise of many who are watching this, is that plain journals actually have less friction going down the track than roller bearings do. And the reason that I came up with, and I think is somewhat logical, is that instead of using journal oil in plain bearings, modern freight cars use grease instead in the roller bearings. And the added viscosity of using grease slows down the car more. And so it's probably not as correct to say that they lost a lot more energy because of plain journals, because they would actually have more friction if they went to tapered roller bearings. And of course, the very first assertion that Hyce came up with, which was whether or not the temperature has an effect on plain journal performance, is correct. That the colder your journal surfaces are, and the more viscous that your oil is, the more friction loss that you'll have because of it. So once you have plain journal bearings up to temperature, it has a lot less friction than if you didn't have it up to temperature. So I want to thank you very much for coming on this journey with me. I know that I had an interesting time trying to create the spreadsheet, along with filming, of course, all the cut-ins that I've shown you. and of course editing this all together. But I hope that you'll come back and watch me in the next episode of West Coast Rail Nerd Reacts to Hyce and kAN's Railroads Online. And I'll see you in the next one. Thanks for watching. Bye.